Now we will continue our discussion of the Navier-Stokes equations with focus on the energy equation. This is based on the first law of thermodynamics. Recall that the first law of thermodynamics states that the increase of total energy in a particular material or fluid parcel volume will be the sum of the heat transferred and the work done on the particular fluid parcel or volume. Here, we will denote our heat flux as Q into the volume, and negative Q dot N as the heat flux into the volume, where N is the outward pointing normal. E will be the specific internal energy. From the Reynolds transport theory of Osborne Reynolds, who was a professor at Manchester long ago, we might write this in the form shown here, which I show in my compressible full class in equation 101. The first particular term on the right-hand side is the rate at which the body forces perform work, denoted by this volumetric integral. The second term is the work done by the particular stresses, Tn, which we discussed previously, in a surface integral. And finally, the third term will represent the total heat flux into the particular volume by partial omega t, another surface integral. We just defined this term on the previous slide, and the negative came out. On the left-hand side, of course, is the time rate of change in the fluid parcel between the specific and kinetic energies, volumetric integral. And there's your balance, first law of thermodynamics. If any particular function f, which is a position and time, we can write the particular equation. You note here that we've introduced a new term t, which we'll describe in a minute. And we can write this new surface integral this way as a volumetric integral. Using the so-called theorem of stress and this identity, we can rewrite 102 with the following, with Tn ui, where ui is the velocity, as a volumetric integral. The transport theorem, which we showed on the previous slide, we can use to rewrite this kinetic energy as a volumetric integral of the material derivative of the kinetic energy with the body forces, the stress, transport, and the velocity stress. We'll define capital tau ij in the next slide. We might interpret this equation as a rate of change of kinetic energy of the fluid parcel or material volume as a sum of the rate at which the body forces are doing work with the rate at which the internal stresses are doing work and the rate at which the surface stresses do work. Let's look at that equation 104 one more time and think about each term and what it physically means. Don't be intimidated by these large equations. Just try and break them apart and think about what each term means individually. If we use the transport theorem and in conjunction with Green's theorem, we might obtain the following equation 105, which is a single surface integral, volume integral of rho times the material or total derivative of the specific energy plus nabla dot q, divergence of the heat flux, minus tau, which we'll define in a second, with the dyadic of nabla u. This is the so-called gradient notation for tau ij u ij in Einstein notation, or index notation, which we defined earlier in this class. Basically, you're taking every element of each particular tensor, multiplying them out, and finding a scalar value. Using these notation, we can now compactly write our energy equation in the form in 106. Material derivative of E times rho, the density, is nabla dot Q, which is heat transfer, plus the dyadic between tau, the stress tensor tau, with nabla U. The Fourier law for heat conduction will generally be used, where theta is T in this case for temperature, and we'll insert that up here based on Joseph Fourier's heat conduction law, which is used almost universally in the field. K will be the heat conductivity coefficient of the particular fluid. Through this insertion, we can simplify 106, which is a boxed equation, so it's important, and obtain 108. Note that K stands right next to the nabla theta, because K might be a function changing in space, which is quite normal, depending on the properties of the local fluid. We'll then define the stress tensor tau ij as negative p plus lambda ukk delta ij, which is the second coefficient of viscosity, plus the first coefficient of viscosity, ui uj plus uj ui. This is the typical form shown in undergraduate fluid dynamics. In compressible flows, we often keep this particular term. This stress tensor was formed with a number of postulates of Stokes, of course, as we discussed way back in the history of this class. And in the next lecture, we'll look at its formation, in particular, the stress tensor. We'll assume that the stress tensor is a continuous function that involves the deformation tensor and the local thermodynamic state, but it will be independent of other particular kinematic quantities, and you can see that in this term. It involves static pressure, P, viscosities, which are probably strongly dependent on temperature itself, the Kronecker delta function, which is just 0 or 1, depending on if K is not equal to J, etc., or I equals J, and then these two particular velocity derivatives with space. Equation 108 in a simplified form for a heat conduction assumption, or more simple form 106 can be simplified given some assumptions. If the fluid is homogeneous or homogeneous, depending on how you say it and where you're from, we might say that the stress tensor does not depend on particular position. That is, homogeneous means that the statistics of the flow, turbulent or not, are invariant with spatial position. If the fluid is isotropic, then the statistics are invariant with rotation at any particular point. That is, they can vary with space perhaps, but the statistics are invariant with rotation. You could also have a fluid that is homogeneous or homogeneous and isotropic, and both assumptions would apply, which simplifies the equations greatly. This is why people in computational fluid dynamics and direct numerical simulations focus so much on these particular flow fields, which are homogeneous and isotropic. If there's no particular deformation of the fluid, then the fluid could be seen, in a sense, as incompressible. Then we can make the assumption, which is Dale and Bayes' condition, nabla.u equals 0. And then the stress tensor would be seen with these particular assumptions as so-called hydrostatic. That is not really moving, so it's not a very interesting case, and we would not consider hydrostatics in these lectures.